And all that system, the whole universe, is expanding. This is a very simple cartoon of what's actually happening because my little daughter, I showed it to her, this is the slide she liked most. She's about 2 years old. She liked it really. And so I'll show it again. I can see that some people find it interesting. But the point here, to illustrate that, is that the people ask, where is the center of expansion, right? So the point is, there's no center. Each point can see itself as a center of expansion. Each of those dots can see itself as a center. People give the analogy of a cake with raisins that's expanding in the oven. And each raisin is getting further away from the other one, or dots on a balloon. In the picture we have at the moment, if you go from top left to the right, there was, we believe, a Big Bang. And the slide says 15 billion years ago. We think it was about 14 now. There was a Big Bang, and there were these tiny fluctuations, back then quantum fluctuations, which you see mapped on that over there. You can see those ripples, a bit like little waves in the ocean. And those fluctuations got then amplified further down and then got projected on the cosmic microwave sky, and then those small seeds created the structure we see today. Okay, so we see an overall expanding universe, but different bits and pieces came together and got amplified under the force of gravity. Now, this is maybe the most significant slide here, because this explains hopefully the title of this talk, that really it seems now, and there's a good consensus about it in the community, it seems now that only 4% of the universe is made of the stuff we are made of. So we belong to a minority, as much as we think for us as being important. Not only we are in a boring neighborhood of the galaxy, but actually the stuff we're made of only accounts for 4% of baryonic, what's called baryonic matter, ordinary matter. There's 21, 22%, and it's called dark matter. When I was a student, we were told it's 4%, but the green part covered 96%. So the picture was, it's baryons and then cold dark matter, which is still hypothetical. We don't know what the cold dark matter is. There are some other examples of dark matter, for example, neutrinos, which we know exists, and I'll show recent results from our group. But otherwise, that's what it is. And then the remaining 74% or so is in the form of dark energy. So these are these two components we don't quite understand. Now, on the left-hand side, this is the other part of the story. In understanding cosmology, you have to see what are the ingredients. So that's on the right-hand side. And then you can ask, what is the curvature of the universe? So the whole analysis of cosmology is done within Einstein's general relativity. And in Einstein's theory, the space can actually be curved. It need not necessarily be flat like this table. And in his theory, the curvature could be spherical or hyperbolic or flat. The data we currently have from astronomy suggests that the universe is flat. It's accelerating because of this composition, and most of it is unfamiliar. So if you can take that as the main message back home, that we know fairly well now the universe is flat. By that I mean that if I shine two laser beams, they'll remain parallel. In a different universe, which is curved, they'll be divergent or convergent. And also that it's accelerating due to that push of the dark energy, and it's really made of stuff we don't know. This is an illustration of that curved space-time. In general relativity, we don't say a star has a mass, but we rather say space is curved, space-time is curved where this object is. So as we like to say, matter tells space how to curve. As a result of it, what we can also see that if there is a real object out there, the distance, it will get, the photon trajectory will be such that it will reach the eye from a different location, so we'll see it shifted. That's called bending of light. It's a well-defined prediction of Einstein's relativity. Now, at lunchtime, I was told I should not put any equations, so I decided, nevertheless, there might be some mathematicians here. So here's a very simple mathematics turning Einstein's equations into a very simple equation. And what it is expressing what I just said, that in general relativity, matter and dark energy tell space how to curve. So what we have here, well, this is just one. Everybody's happy with that, I hope. Here is we have the fraction of stuff in the universe in the form of matter. So it's this, whatever I had there, 22% plus 4%, 26%. For now, let's call it a quarter. It's the fraction of, at present. And this is the fraction of this dark energy we talked about. And as you can see, if we know the two of them, we can tell the curvature. So as it turns out, the current numbers are such that the curvature is 0, and it's made of, it's influenced by the contribution of matter and this dark energy, which I still haven't told you what it is. Now, in order to challenge the mathematicians in the audience, I thought I'll do one mathematical operation. So forgive me for that. A very complicated one. I basically move that term from the right-hand side to the left-hand side. Is this okay, Patricia? Correct. Well, this is actually quite an important illustration of what Einstein's theory tells us. Because when I turn it to put it on the left, it means that this dark energy is not actually energy, but it's just a correction to the curvature. So this mysterious component, either there is something out there, either every centimeter cube in this room has got this dark energy, or space is not exactly flat as I told you, but it's got a little deviation from it. And that's what we don't know. If you look at the literature day to day on the electronic archives, you'll see some papers claim we see dark energy, other papers would say we see curvature. And just for completeness, I put at the bottom actual Einstein's equation. And it's interesting that he actually put lambda, which is this symbol for dark energy, or as he called it, cosmological constant. He actually put it on the left-hand side, not on the right-hand side. It's interesting. But it's really putting on the left and right changes your whole concept what it is, however trivial it may seem. Now, I'd also like to talk, it's quite a diverse audience, so maybe it's good to talk a bit about scientific paradigms. When I was an undergraduate, I was exposed to this famous book by Thomas Kuhn, The Structure of Scientific Revolution, where he said that science undergoes periodic paradigm shifts, and it's not just progressing in a linear fashion, and that this really, suddenly there is a discovery that changes the way people think. And it's really, I think, only when I got myself into research dark energy, I could see what Thomas Kuhn actually meant, because I could see how dark energy cosmological constant was in and out of fashion. I also like very much the third bullet points, that scientific endeavor is very much is not just relies on objectivity, but we must account for subjective perspective as well. And I have plenty of examples, there's no time to tell them, that how the subject is actually affected by sociological and psychological effects. It's not just doing computing. That's why I like to show people, talk about people, not just about the equations. And here are some of the heroes of this, and it says the chequered history, because this cosmological constant, as Einstein called it, which now got the glorified name dark energy, you know, it sells better, especially when you're trying to get money from the Department of Energy in the US. It's nicer than cosmological constant. It's a general form, but it's very interesting. Einstein put it there as a way of getting a static universe, because his solutions gave either an expanding or contracting universe. He didn't like it. Again, here is your subjectivity example. Why didn't he like it? We don't know. So he said, let's put a constant. A few years later, Hubble showed that the universe is expanding. So Einstein said that this was the biggest blunder of his life. He probably said something like this in German. We don't quite know what he said exactly. And then it was said to be 0. So when I was a student in Cambridge, I was told we know it is 0. And now people think it's not 0. And it has an embarrassing value. Why is it 75%? We don't know. And the actual value, anyhow, is very small compared to some theories from particle physics. It should have been much, much bigger, 10 to the power of 120 bigger, according to some theories of early universe. So that's embarrassing. It's also embarrassing how come we live in a universe where dark matter, dark energy are in similar quantities. So this is all the way from Einstein. The two people you see on the right are people about my academic age. They led two teams that studied supernovae, exploding stars, and in '98 claimed that there is a need for this cosmological constant. Although you can also see already in the literature papers about cosmological constant, including by myself, in the early '90s. I should also mention, because this is a broad audience, which includes historians and people from other disciplines of science, that's quite interesting. Most people would tell you dark energy is 10 years old, 98 or so, 12 years old. I would say, oh, Einstein talked about it. Here is just an example that shows that, in fact, Newton actually already suggested something which looks like cosmological constant. He had this term here, possible term, which goes like force being linear with r. We're all familiar with force, gravity falling off like 1/r squared, and Newton also considered, for reasons I don't have time to explain, a linear force. And his biggest mistakes was not to call the constant lambda over 3 and not to consider superposition. Otherwise, we would have credited him with that. So if you want just to get your intuition what dark energy is, one way of thinking about it is we are used to minus g over r squared. We trust that as the force. That's why apples drop. And when we take an airplane, we trust it. Otherwise, we wouldn't arrive safely. But actually, it does mean in the modern science that, in fact, the true force also has another repelling force, which goes like distance, except it's so small that it's noticeable only on very large scales. So on the solar system, it's not noticeable, and all the computers that calculate trajectory of airplanes ignore it. It's so small. That's why it's called cosmological constant. It's all quite nice, and Newton was quite excited. It's allegedly the only place in the whole of Principia where he expressed emotions by saying he discovered two forces. And in fact, with a master's student, Lucy Calder, we wrote an article about it. It appears on my website if you're interested. And also another article about the paradigm shift 20 years ago. So you're welcome to look at that history. So what is dark energy? I kind of told you either it is some sort of energy which technically is called vacuum energy, and this is parameter W for the physicists in the audience, which is the ratio of pressure to density, which in Einstein's theory is just -1. There is now effort by hundreds of scientists, which would cost billions of dollars or pounds or euros, to actually measure that W. Huge effort to measure that W to see, is there a deviation from Einstein's prediction or something else? There's the possibility of it being all on the left-hand side, modified gravity, or maybe our concept of uniform universe is wrong. We don't know, and this leads to all kinds of other ideas. Maybe we live only in one universe and there are many other universes, multiverse, and some of you are might familiar with the concept of anthropic principle, which means that the universe is the way it is, otherwise we would not be here to discuss it. So it has favorable conditions for our life. And that's a summary. I hope I managed to give you in 30 minutes. I was trying to squeeze in a soft course we give in 33 hours on cosmology here. But the main message here is that there's lots of observational data now. Unlike in the old days that it was more of a metaphysics that you could just hypothesize, now there are really data sets which eventually will have billions of galaxies. And what's remarkable that these different data sets, cosmic microwave background, supernova, galaxies, and so on, coming together suggest actually there's agreement on the observations, but they all lead to a very bizarre universe. A bizarre universe that, in fact, the stuff we are familiar with, myself and the desk and you, only 4% of the universe, and then about, in total, about 20-something% in cold dark matter, and the remaining 75% dark energy. So we would like to understand it, or maybe we are completely fooled by nature, and it's not dark energy, but Einstein's theory needs modification. But I would only say that apart from looking for a new paradigm shift, that this service would be extremely important for measuring other things, because you get huge maps of the universe, and you can look at stars and galaxies and Milky Way. And I can only finish by saying, I wish I could guess what Christopher Wren would have said had he known about dark energy. Thank you very much.